The multi-stability landscape, right? Energy landscape can guide the structure to move into the configuration. I don't have to control each part, right? By iteration, right? The land energy landscape is gonna have this attraction domain, right? To do that. So that was the imagination. When I just shared with them, people just feel like, wow, are you crazy? Like a daydreaming. So okay, to be honest, they didn't believe me at first. I was having a hard time at that time. So and then so let me just clarify the design problem. Is that given the mechanism, this is the mechanism provided, let's say, and then we introduce, right? It's a multi-stable mechanism. How can you change it into a multi-stable structure? It has to be a structure, right? It has to be an energy in it. So I say, oh, how about we just introduce torsional springs at each of these creases? But those are designable springs, right? I can design the stiffness of each one of them. I can design the rest angle of them. What do you mean by rest angle? Is that I can pre-rotate it, right, to the angle I want, and then I mount it on top of it. So those are the design parameters. The rest angle and the stiffness of those torsional springs. So what do I want? I want this N configuration, let's say 3 for now, to be stable, just by design. That's my design target. So is that possible? So I started with a rather simple example to see, oh, is it possible? So here is a 4-bar linkage, right? And then we mount 2 torsional springs on it, right? It's really simple. And then this theta A and the theta D, we use these 2 parameters to track this motion of the 4-bar linkage and also the energy of these 2 springs. But these 2 springs are a little bit special, is that I preload it. So it has a rest angle at 1.5 pi. This one has this rest angle. What do I mean? It means that I pre-rotated to this angle, and then it has a rest angle at this, and then I pre-rotated to this angle, and then I mounted on it. So there is pre-stress in it. So and then another thing is that we plot it in this space. X-axis is this theta A, this is theta D, and these 2 parameters are sufficient in reflecting the kinematic path, right? That's the mechanism. Because they are not free. They're mounted because it's a 1 degree of freedom. If they don't satisfy this relationship, the 4-bar linkage will just break apart. So that's one relationship we have, but also the energy, right? These 2 springs are also sufficiently described by this plot, all right? By this 2 dimension. So that is that, because I said, oh, this is the rest angle, so which means at here, if the 2 springs are in this configuration, there's no energy, right? That's the global minimum of energy. So when you move away from this point, then you have this equal potential, curve going up, right? So when you move away from it, energy will just increase like a quadratic energy, like a ball. So you can notice, okay, actually it's a bistable structure. Why? Because you see there are 2 points that are kind of tangent to this equal energy surface, right? So it's a bistable structure. I kind of found out, oh yeah, you see, it's bistable. Okay, but what can we do for that? We want to design, right? I want to prescribe the location of stability. So we can do it inversely by just graphically. Let's say I want to move my target point, stable state, to here and here. I can just draw this line. They can meet here at O. So now if I just change the rest angle of my torsional springs to this value, this incorporated structure will be stable at these 2 states. Okay, that's the core idea. That's the core idea. But so there are 2 things. So one thing is that, oh, you can at the maximum, right, make bistability. That's correct. No, that's not correct. Because that's you draw the line, right, you meet, but this is in 2-dimensional space. What if I have 3 springs? What if I have theta A, theta D, and another theta B? Right? What if it's in 3 dimensions? Right? I have three springs. I mount another spring here. What will happen? So at a given point, when you draw the normal, it's not a line. It's a plane, right? The normal is a plane because in 3-dimensional, you have a curve, 1 degree of freedom, right? Select a point when you draw the normal. It's actually a plane, right? So you can have 3 stable states when you have 3 springs. Because 3 planes, they meet, there might be a solution. So when you have more springs, there are going to be more stable states. That's the first thing. And the second thing is that, oh, we are doing it graphically, right? I mean, we cannot draw that in 4 dimensions. And what I'm going to do, we write equations. So there's a complete analytical method describing how to have this tangent, right? How to do this normal, how to just compute, just like quite general in this paper. I published it with Professor Pellegrino. So the full theory is in that. I'm not gonna go into details. So I'm just gonna move on to examples. So this is the first example. We have a non-flat origami, and then I provided these two target configurations. I said, okay, I want these two to be stable. So now here are my equations. I want to just briefly mention that this phi 0 are the rest angle of those four springs. There are four torsional springs. And then how much I pre-stress them is the unknown, right? It's the variables that I want to solve. So these two equations basically describe tangent, and then it should be orthogonal to the force that you receive. So it's just describing the equilibrium. So this is describing the stability. Basically, it's just describing the curvature, right? So when you draw the normal, it should be on the basically concave side, right, instead of on the convex side. So that's describing the graphical thing that we were doing in that drawing. And then we have a target function, basically minimize the pre-stress, and then it's a quadratic programming problem, and then we can solve it. And this is the solution. Basically, it's telling us that how should we pre-stress four of our springs, torsional springs at these joints. Okay, and then MATLAB tells us, okay, it's bistable, great. So now the problem here is how to manufacture a torsional spring with prescribed, okay, I just want to make sure that I have the right timing. I have like 8 minutes. The difficulty is manufacturing. That's what I'm saying. So I just built, I kind of learned from the door hinge, right? I have torsional springs, and then I have these two basically, you can notice I have a lot of holes. So I need to kind of turn it to the right degree, and then the right holes will just match each other, and I insert a pin in it to kind of keep the right rest angle, to manufacture the right rest angle. I also made some efforts in reducing the friction with this polished surface and with the bearings and so on. I did a lot of stuff. So this is the prototype that I built, and it's really hard to manufacture, and it's quite heavy, and also with large friction. But gladly, I convinced everyone that it's true that it's happening. I gave to my supervisor at that point, everyone was convinced at this point. But the problem is very hard to manufacture. Actually, I still remember, I have everything delivered, all the parts printed. When I assembled it, it took me 5 hours, just assemble. That was the difficulty at the time. So I made some improvement on simplifying the manufacturing, but how? How is because this guy is hard. The rest angle, right? To manufacture given rest angle is very hard. And then, so I want to just use this. I can just set some simple values for the rest angles, basically 0 or plus negative pi. And then I solve for k. I chose a different set of variables because k actually is easy to design. So now I just rearrange the equations a bit. So the k is now the variables, and then the phi 0 are given, right? I just tentatively give some values here. If it doesn't work, I change them. So, and this is again the same principles, but the variables becomes different. So now I solve for a bistable mirror. Actually, this is the one that I'm giving to you, just like passing around. So this also tells us that it's bistability. So now I want to answer why K is easier to manufacture, because I also had this idea. Say at that point I realized, I noticed the work from Professor Larry Howell. They are doing this latch joint. So I realized, if I just cut these beams differently, I can actually prescribe the stiffness that I want for the joints, right? And actually it's a video. Let me just play them. So, but how do you do plus minus pi? This is how I did it, right? The rest angle is pi. And then you can also add some contact on it. There's some of my previous colleagues contributed into manufacturing this, and that's that. So that's the new version of those torsional joints. And I manufactured this bistable mirror, and I'm just also passing around. This mirror is, you can see, is bistable. Okay, but you can probably sense the problem here is that the stability is not very high. And then we move on to this, the real thing that we want to do this 3x3 at first. So Professor Pellegrino actually presented some of this in his talk, but he was presenting 5x5. So at the moment I was working on it, I only just finished the 3x3. So it passed on to the colleague who is taking over my job. Okay, we're talking about my work actually. Okay, so this is the 3 stable states. You can also notice we add some clips we'll try really hard to improve the stability. So now I really just realized what I imagined. Use 3 actuators, 3 cables, and to maneuver. Maneuver across those 4 target configurations. You can see this is going to be snap out to be at the spherical shape. You can see that's spherical. And sorry, I don't want to take too much time for this. So it's spherical, and then when you pull this one, I have like 3 minutes. Okay, so okay, it snapped back to flat. And then you can also do spherical. Oh, sorry, like a what is this? Like a cylindrical. Okay, cylindrical, and then also be back to flat. So, okay, a short conclusion for this is that multi-stability can really simplify actuation, right? From 12 actuators, now we reduced into 3. That's great. And so, how did I come up? Alright, well, what is composition of this multi-stability? It consists of rigid mechanism, which is the skeleton, and also pre-stressed and designable springs. And this can help us to have the prescribed, prescribed multi-stable configurations. The problem, which can be reflected here also from earlier the talk of the Caltech Professor Pellegrino, that they have low stiffness. In here, I mean, in the end, when they do the test, when they did the test, they use a lot of wood strip to reinforce it. You can see the cardboard here. They need to kind of hold it. So it has a huge problem of this stability. And also it's quite hard to manufacture still. So I carried on this topic on multi-stable structures and to try to tackle that problem. And here are some preliminary videos. You can see this one is a 3 stable structure, and now noticeably they can be more stable. Okay, and this one is another 3 stable structure, which is more complex, but also we can prescribe the stable configurations. So here is another 3 stable, actually 4 stable structures. So we're looking also into some other applications, like moving wings, robotic platforms with impulsive motion, and so on. That's it, I guess. Okay. So also we are moving now into 3 dimension for some multi-stable spatial linkages. As you can see here, we are also developing it into a impulsive gripper, and also we're making attempts to make it like a jumping. Okay, but it's really not for now. But we're just trying to make something, trying to make use of it. And here is another one. Is we also realized that we can also do multi-stability in the panels. This is a bistable thing, and here is another one that is also bistable. Oh, and I think they are passing around, so you can just check them out. Here is also another bistable one. Here is another bistable one. Okay. I think, oh yeah, I would like to acknowledge my supervisor at Caltech, also some previous colleagues, and also my current students, and at Wuhan University, so I really appreciate the help. Okay, and then that's all from this talk.
Okay. Okay, Professor Li, maybe we could have a very quick question from the audience. Any questions?
Yeah, please, Professor.
Oh, very interesting. So when you were having design,
the pre-stress, I mean the turn that you used as an input parameter, for example, like 3 pi and the 1.5.
Yeah, right. I use it as an input parameter now. Yeah, like previously it was a variable, but now by the second version, I use them as preset parameters, and I solve for the stiffness. Stiffness you can cut, right? That's easy.
But for example, metallic joint,
Mm-hmm.
it's not so easy to have, let's say, prescribed
Stiffness.
not stiffness, but zero energy state, right?
You mean the rest? Yeah, you're correct.
Yeah, either
correct.
zero angle or 180-degree angles that you choose, right?
Yeah, I only have two options. You are right. Just either you are flat or you are completely closed.
But can you again do some, instead of using a spring steel, you use just the stainless steel and do some
Heat
post-processing?
treatment. Got
Yes.
it. So did you ask this question like when Pellegrino was presenting? Yeah, I agree. Like maybe you are talking about something like this. Let me just play this one. You can have any intermediate state if you just join them with an angle section. You can see. Yeah, you can do something like that.
That's more like hard to stop, right?
This one is like a hard stop. This one is like a hard stop. Yeah, you can see the hard stop is here, but this one is that they are connected through an angle section, so you can build it into whatever angle you want. It will rest at that angle. Great. Yeah, thank you so much for the question. Yeah.
Yeah, okay, so very good. Yeah. So you have some prescribed some shape, right?
Mm-hmm.
And then try to have some stable, right?
Yes.
So and then you control the pre-stress with some torsional stiffness.
Yes.
So we may call that this one can be called inverse design, right?
Yes, I think so. Right. You prescribe the target shapes, right? And then I compute for the design parameters.
Right. Absolutely. Yeah. Okay.
Thank you so much. Thank you.
Okay, let's thank Professor Lee again for